Hi class, we are on to section chapter 12.2. We're going to discuss classical PDEs and the boundary value problems that come along with them. So there's basically three classical PDEs. Those are the heat equation, the wave equation, and Laplace's equation. So we'll talk about the three of those. Their origins are all pretty interesting. The wave equation obviously is applicable to quantum mechanics, so that's very important in its own right. The Laplace heat equation is very important as well for heat diffusion. So is obviously the heat equation, right? So we're going to have the heat equation in one dimension, the wave equation in one dimension, and Laplace's equation in two dimensions. Okay, so for the heat equation, we have a constant multiple of our solution function u to the second derivative with respect to x equals the derivative of u with respect to time. Okay, so basically what's going on here is that our u function is a function of x and y, but x and y are parameterized in terms of t, right? So heat diffuses along x at a, and it goes over time, basically. Okay, that's the easiest way to talk about it. So we're going in one dimension, so it's not actually x and y here. It's actually just x, but with respect to time. How does this heat flow through my object in one direction, along x, as time progresses? So we're going to say that we have a thin circular rod of length L, where each two-dimensional cross section has an area of A. Basically what's happening here is that the rod is uniform. So the area, the cross-sectional area, does not change, right? So it has a uniform width, basically, or a uniform radius, I guess you could say. Okay, so as such, so we have a length of L. It's uniform. It's not a rod that has varying height, right, or varying radius. And so through a single cross section here is A. So again, A is not this volume. It's just the area of a single cross section. So some of the assumptions that we have is that as heat flows through this rod at time t along a position away from 0 of x, that's our function that models that. Okay, we say heat flows only in one direction. So again, there's no y value here. We're not talking about its height or anything along those lines. Just we're only modeling heat as it flows in this direction. Okay. No heat is escaping from the rod, so you can assume that it's inside of an insulated container. Okay, but for simplicity, we're only talking about the flow through the rod itself. Okay, so all the heat is contained within the rod and does not escape. No heat is created within the rod. Okay, so we say that the mass per unit volume is rho. So the rod has a constant mass, right? It's not varying in mass along itself. So mass per unit of volume is rho. Okay. Gamma is the specific heat, and K, capital K, is the thermal conductivity of the rod. So how well does it conduct heat? And gamma is the heat being applied, right? Or the heat at the time. Gamma and K are constant values. Okay. Real scalars. So Q, which equals gamma times mass times our function U, is the quantity of heat in an element of mass m at temperature U. Okay, so the derivative with respect to time is negative k times the area times the rate of change in the x direction. Okay, this is the heat, the rate of heat flow through a cross section A along x, which makes sense because it's the change in the quantity of heat with respect to time. Makes sense that it is the conductivity times the area, so the conductivity over the area with the rate of change in the x direction, right? So that's the change of the quantity of heat. And so our mass here, right, is the mass per unit volume times my area times the change in x, right? So it's basically my mass times that cross section over here. So A delta X gives us a volume, and then that is the mass per unit volume over that portion of volume, right? And that will give me my mass. So that makes sense as well. So this implies that Q, once I substitute my value of M, right, my equation for mass here, is gamma times my function U, right, which gives me the flow of heat, right, what the temperature at the position given time. So I have gamma, my specific heat, times my mass, times my value of U. So now if I take the derivative with respect to T, again, delta X and U are those things that are have to do with time, right? So specifically U. So X is an independent variable, U is a function of X and T, so X just depends on X, U depends on both, right? So the net heat flow is the difference from a little bit beyond X and my initial point of X as far as the rate of heat flowing between those 2 points, right? So this is Q of T here from X and a little bit past X, right? So that difference will tell me the net heat flow. So how much is flowing from this as my starting point to this point, just a little bit beyond, which is delta X. And so when I make this difference, right, I have a constant of Ka that I can pull out, okay? And then here I just have the difference in my U sub X, right? The derivative of U with respect to X from one point to the other, right? So this can also be substituted, right? This net rate of change as my gamma rho A times delta X UT, right? That's the same thing here. So equating that on both sides and then solving for my U of T function gives me the following, right? So I divide everything by gamma rho A and delta X. So here I have K and A, so those A's will cancel, K stays, gamma rho stays on the denominator, and this delta X can stay with this function. And again, if you notice, this is the form of a derivative right here, right? So it's the net, it's the rate of change of the derivative with U to X, U with respect to X, over delta X. So when we let delta X get small, this turns into a second derivative with respect to X, right? So the thermal conductivity over gamma rho U double X is equal to UT, and that's the equation that we started with in the beginning for our heat equation. So that's our derivation of the heat equation through a rod, okay? Here we let little k equal this constant because this is just a constant anyways. So we get that equation that we had, okay? So little k, this thermal conductivity over the specific heat over the mass per unit volume is the thermal I'm not going to be able to say this, diffusivity, the rate that the heat diffuses from the rod, okay? That's an easy way to say it. So for our wave equation, we're not going to go through a full derivation like we did for the heat equation, but that just gives you kind of a sense of how these things are derived, okay? So for the wave equation, we'll start with the equation as well. Alpha squared, the second derivative of U with respect to X is equal to the second derivative of U with respect to T. Right, so we'll just talk about the assumptions that we're making, but we won't go through the derivation here as well. The wave equation can be derived in several different forms, and when we use a different coordinate system, right, it helps us to model different things. So right now, our wave equation is really modeling the vibrations of a string. If we change this into spherical coordinates, then we can model some quantum mechanics, right? We can model the wave equation over an atom. So here we're going to say that we have a string of length L such that each point on the string moves orthogonally to the x-axis. It moves up and down with respect to the x-axis. It does not move left or right, only up or down, okay, when it's stretched and vibrating. Okay, so we have it held tight at 0 and L. If we were to pluck this, for instance, the string vibrates up and down. Okay, it doesn't vibrate side to side, only up and down. Okay, so here u of xt is the height of the string above the x-axis at some value of x at time t. Okay, our string is flexible and elastic. The string is uniform. Okay, very important that we don't have changes throughout the string as we go along x. Our height is small compared to L at all points. Okay, so we don't have, it doesn't vibrate close to or even along the, close to or bigger than the length of the string itself, right? Which is, again, why it's being stretched and vibrating. Okay, the slope of the curve is small at all points. Okay, so again, this slope here has this a small rate of change. The tension, which we call T, is tangent to the string. We've seen this before in previous sections. Here we're going to call the magnitude of that tension, of the tension vector, capital T, right? So there's a difference between the boldface and the non-boldface. So again, this is a scalar. It's the magnitude of the tension vector. And it's going to be the same at all points. Okay, there are no elongated segments. So that delta S that we're looking at here, okay, just this small little portion, the tangent vectors to those are here. So again, this curve continues on this way, right? And these T1 and T2 vectors are the tangent vectors at the point X, and in this case, the point X plus delta X. So a little bit away, okay? T, the magnitude of the tension vector, is large compared to the force of gravity. So gravity is negligible for our calculations. There are no other forces acting on the string, and the weight of the string is small compared to the tension vectors, okay, or the magnitude of the tension vectors. So here we say that alpha squared is the magnitude of the tension vectors divided by the mass per unit volume along the string. Okay. For Laplace's equation, okay, we have the Laplacian squared of our u function equaling 0. Okay, so what this is the second derivative of u with respect to x plus the second derivative of u with respect to y equaling 0, right? If we're in 3 dimensions, we would have u with the second derivative with respect to z added onto this as well. Okay. This is a time-independent model, so t is not a variable here. It only has to do with x and y. So we're modeling, in this case, the heat flow through a plate, not as time progresses, but just at different positions, right? So we'll talk about this later with our initial conditions and our boundary value conditions. But if we have, let's say, a hot plate, either heat is being applied uniformly, or perhaps heat is only being applied at an edge, right? So basically, our function here, xy, tells the temperature at point xy on the plate, right? Not as it changes over time, just where is the heat at, okay? So this is an example, okay? Here it's insulated on the boundaries. This isn't standard, right? This would just now give us some boundary conditions, okay? Which we'll talk about later. So, initial conditions, and this is not initial conditions for Laplace's equation, this is just initial conditions, period, okay? Just in general. So, if I have something of the form ux here, time being 0, or in this case, it could be y being 0, equaling a function, or maybe it's the derivative with respect to time, where x is free to move, but time is 0, right? That's an initial condition if my function is x and t, right? So t being 0, x at any point is equal to g of x. Here, the derivative of t, time is being 0, x again free to move. These are some examples of initial conditions. There are all kinds of combinations possible for us to make, okay? Same with boundary conditions. There's all kinds of different boundary conditions we can make, and they can be mixed in with initial conditions just like in previous sections. So boundary conditions basically fall into 3 categories, okay, which we'll talk about. So some examples of those could be at the boundary at x equaling 0, t free to move being 0, or at the boundary of L. So these could be conditions for a vibrating string. They could also be representative of boundary conditions of a rod, right? The start of a rod or at the end of a rod as time goes forth, right? So maybe if this was a rod, for instance, the heat is always 0 on both ends, no matter how time continues on, okay? So for a string, this makes more sense that there is no height at either end of the string because, let's go back here, right? I am held in place, okay? And then the rest of this is allowed to vibrate above my axes, okay? So you can think of a guitar in that case, or any instrument, any string instrument really. So that's an example, okay? So on a boundary, only one of the following can have conditions imposed in the boundary types, okay? So one is on U itself. These are called Dirichlet conditions, okay? If I am imposing a condition on a derivative of U, here n is one of the independent variables, x, y, t, whatever it is that I'm using. These are called Newman conditions, right? Here n is one of the independent variables. If I have a derivative of n plus some constant of my function, right, then these are called Robin conditions, right? So here's some examples of some boundary conditions. So we'll stick to the example of heat flow through a rod just to make it easier to understand for this case, okay? So if I have a boundary condition that my rod at 0, so on the left side of my rod, no matter how t goes on, is equal to some function, right? So I have some function being applied to the temperature at the left-hand side of my rod, and as t goes on, that heat function fluctuates, right? So whether it is that I'm cooling it down as time goes on, or I'm increasing the heat as time goes on. And I can do it as well to the right-hand side, right? The end of the rod. That could be equal to a function, right? The heat is increasing as time goes on the end of the rod, or it's a decreasing function as time goes on, or it's a constant function. It's being held constant, okay? So you could think of that, if you come back to this rod, as maybe I'm applying a flame to this end of the rod, and maybe I'm applying a bigger flame or no flame, or this is being cooled in some way on either ends of the rod. So how is heat flowing through my rod if I'm applying heat to one end, either end, or if I'm cooling, I already have a hot rod and I'm cooling this down as time goes on? How is my heat flowing through my rod? Okay, so that's an example of a heat condition, or a boundary condition, I should say, on a rod. Okay, so that is on U itself. That would be a Dirichlet condition, right? So if I'm doing it on the heat flow through the rod at either time, I'm now looking at what's happening heat flow wise, right? If there's no change in the heat, right, then I'm insulated on either end, okay? There's no flow coming in, there's no change in the direction coming out, right? So that would be a Newman condition. And then here I have these convoluted questions, right? So here at this boundary, I have a negative h times u0t, so that's still at the boundary, minus some function, and maybe at the other side I have the same sort of thing. So here, if h is positive, we can talk about what's going on, right? So this indicates that the ends are in a moving fluid or a medium, which could be a gas, right? Cold air, cold water, right? Some sort of gas that conducts heat well or does not conduct heat well, right? So if u of 0 is larger than this function, right? So what's going on here is that this is larger. This is going to give me a positive value, and then it's going to become negative, right? So ultimately, the condition here is that I have something that is decreasing, okay? The bar is hotter than the surrounding medium. So this G1 is the function that has to do with the medium. this is the temperature of the bar, right? So the heat will flow to the left. That's why it's negative. The bar is hotter than the medium, so it'll flow through the rod. Okay. Here, if it's cooler than the medium, okay, then the bar is cooler than the surrounding medium, and heat's going to flow to the right in the positive direction, away from the cool. If the boundary on the other end, right, is larger than the gas surrounding it or the medium, then the end of the bar is hotter than the surrounding medium, and the heat will flow out of the bar to the right, towards the cold. Okay. And there we go. So that's an example of our conditions on a rod. Okay.